Hello there and welcome to a look at ES1.2. It is called the reactions of halogens and halides, and this is a follow-up to the when we looked at the properties, both the chemical properties and the physical properties of the halogens. So you need worksheet ES1.2. This is something that we have had to get a license for to use, therefore I'm not allowed to share these online with anyone who is not doing our course, who has not paid the license for that. So this can only be shared with our class. Okay, let's have a look first at the worksheet itself and what we should have been having a go with. Okay, here it is, ES1.2. In this activity, we're going to explore the reactions of the halogens and their compounds. The reactions involve colour changes, so if we were doing this in lesson, you'd be able to take photographs, but I did send you some videos, so hopefully you have actually seen those things happen. Blah, 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 blah. Some lovely background stuff here. Hopefully you've had a nice read of those. This is the equipment that we would have used. Safety. Can we see here, ladies and gents, our halogens are not nice. Toxic, in fact. Okay. So what we would have done is put a little bit of chlorine water and bromine water and iodine solution, so iodine water as well. All three of those are aqueous solutions and therefore they will have a specific colour. So let's have a look what observations we would have been making. So in an aqueous solution, the chlorine is not that easy to see. In theory, it's supposed to be a pale green. However, in a moment I will show you the picture of what it actually looks like and you'll see that it's a fair way off that. The bromine water should have been a sort of orange yellow colour, and in aqueous solution, i.e. water, the iodine should have been brown, which is a little bit upsetting because we think of bromine as being brown, don't we? But hey ho. Now, then you were asked to add cyclohexane to each tube. So cyclohexane is what we call an organic layer. And sometimes chemicals dissolve differently in aqueous solutions to what they would do in a organic solution. Mr. A is looking through some of that, I believe, with you soon. It's all about the induced dipoles, intermolecular forces of attraction, all that sort of stuff. Okay, so in the organic layer, what we should have seen for the cyclohexane with the chlorine, again, it is that sort of pale green. Bromine, I like the alliteration, bromine goes brown in the organic layer, and iodine, which is my favourite halogen, because it goes violet, which is just a la-di-da way of saying purple. The examiners do prefer you to say violet instead of purple. On my screen right now, you can see what the halogens look like in their elemental form. So the chlorine here, as I said before, you can't really see an awful lot. At room temperature and pressure, chlorine in its natural state is a gas. Therefore, look at this, you can barely see this. There should be a very, very pale yellowish, very pale greenish colour right there. It's not particularly easy to see. Whereas the bromine, there we go, the bromine's got that browny orangish colour that we know and love. I was going to say, I'm not sure if love's the right word for it, but that we should know of. And bromine at room temperature, bromine goes between being a liquid and a gas. It evaporates and condenses, and if it is in a sealed vessel, this will continue happening in what we call an equilibrium. Iodine, as I said, my favourite halogen. If you have it in its elemental form, it is a greyish charcoal colour solid with a slight shine to it. It's quite pretty. But when you start heating it, hopefully you got a chance to see this in lesson. I'm gutted for you if you didn't. It gives off the gorgeous violet purple vapour, which is just absolutely beautiful. And if you do it in a sealed container and you get high enough concentration, it does end up looking like Cadbury's chocolate purple, which obviously I'm going to love that. So that's them in their elemental forms. This picture here shows both the cyclohexane, the organic layer at the top, And the layer at the bottom is the aqueous layer, i.e. water. So you can actually see here already there is a massive difference between the appearance in an organic layer and in water. From this, I'd like to think you can go, okay, that must be chlorine, that must be bromine, and that must be iodine. Do not forget all our halogens are diatomic, so they are all there in twos. So here we can kind of see the start of a very, very, very pale orangish brown. And with the iodine there, we can't really see the brownish colour that it should go in the aqueous solution at all. It is very tricky to see. And for that very reason, that is why a lot of the times we use cyclohexane to show the presence of the halogens in a solution, because it's easier to detect than it would be in an aqueous solution. So that's what they look like, both in the elemental form, aqueous form, and organic form. Let's have a look at the first load of questions. 1A. Use your observations from the experiments on the solubilities of halogens to comment on the relative solubilities of halogens in water and in cyclohexane. I'd like to think that it's relatively clear that the halogens are significantly more soluble in the organic layer. Extension task here, if you fancy it. Think of Mr. A's lessons. I'm not entirely sure if you've done solubility yet or not. If you have, great. If you haven't, don't worry, you're going to come on to it soon enough. Have a look at the solubility of these compounds and see if you can figure out from, in terms of ID, PD, PD, and hydrogen bonding, why the solubility of these things are the way that they are. B. It says, when and why might it be useful to make use of the solubility of bromine and iodine in cyclohexane? Just as I talked about before, the organic layer, it shows up significantly, a significantly stronger colour than it does do in the aqueous layer. And not only is it a stronger colour, but they are different colours as well. So in the aqueous layer, it's tricky to tell apart the iodine and the bromine. However, in the organic layer, it's blatantly apparent which one is the iodine. So our answer for B is going to be that it is easier to identify the halogens in the cyclohexane. So we could talk about there being brighter colours. And actually, this is especially true when you have quite low concentrations. And that is an example where it is particularly useful. Even in low concentrations, the colours show up really nicely in cyclohexane in the organic layer. They do not show up in the aqueous layer. Okay, let's have a look back at the questions. Reactions of halogens with their halides. So these are just displacement reactions, and these are, we talked about these way back in GCSE in year 9 and in year 10 at our school. And actually, based on reactivity series that you should know about, this should be really easy to do. So in 2A, what is happening when chlorine is reacting with potassium bromide solution? So KBr AQ and AQ there. This should be pretty obvious. The chlorine is more reactive than the bromine. So that chlorine is going to see that bromine with something very nice there and go, no, you know what? I'm going to have that potassium all to myself. So what we get being formed is bromine gas. The poor little thing goes off by itself, and the chlorine becomes chloride and steals the potassium for itself. Now obviously that is not balanced, but to get it balanced, all I need to do is 2 and 2 there. In this case, the bromine is given off as a gas, but they probably would accept it being aqueous as well. B, ionic equations representing the change that takes place. If they are looking for an ionic equation, we're looking for weird charges being there, but not necessarily the electrons being shown up in a big way. So we're basically having the ions, but no spectators. So the spectator in this case is going to be the potassium, because the potassium has just moved from one place to another. Its oxidation state has stayed the same. So our ionic equation is going to be HCl plus, the ionic bit in this that changes is the bromine. Now, well, I say the bromine, it's bromide, isn't it? Because it's potassium bromide there. So Br minus. And then that's going to change to Br2 plus Cl. Now this chlorine has changed from chlorine atom in its elemental form to the chloride ion in its ionic form there. So that is the ionic equation to represent the change that takes place. C, half equation to represent the changes taking place. It's just taking this equation and breaking it down one step further. So let's have our chlorine there becoming chloride. There's two lots of chlorine on the left hand side, but only one on the right hand side. So let's balance that first. There's two lots of minus on the right hand side, so there needs to be two lots of minus on the left hand side. We'll do it for bromide going into bromine as well. So Br minus becomes Br2. There's two bromines on this side, so I need two bromines on that side. There's two lots of minus on this side, so I need two lots of minus on that side. Describe what happens in terms of redox changes. Okay then, let's do this, but let's just make it as easy as possible. So for the chlorine here, it's gone from an oxidation state of 0 to -1, or you could say that it has gained electrons. Therefore, the chlorine has been reduced. So that's all that I'm going to do for that part of part D. I'll do the same for the equation below as well. So our bromide here has gone from a charge of -1 to having the oxidation state of 0. So oxidation state of -1 being converted to an oxidation state of 0. That is an increase, or we could say that the bromide has lost electrons there. Oxidation is loss, and increase of oxidation number is also oxidation. So in this case, this reaction shows the oxidation. The rest of these are relatively straightforward to do, so I am going to whiz through them at quite a pace. Feel free to pause. If you do have any questions, please do send me a message via Edmodo or the school's email address, or even on the comments for this video. So in 3A, we have got chlorine water being added to potassium iodide. The chlorine is more reactive, so the chlorine is going to displace the iodine and take the potassium for itself. So what we're going to have happening there is iodine being left out on its TOD, and you've got potassium chloride being formed there. That is not balanced, so let's get a 2 there and a 2 there. That is now balanced. So B, it wants just as we did before, the ionic equation, so get rid of the spectators, so Cl2 plus I minus goes to I2 plus Cl minus. Half equations, Cl2 goes to Cl minus, the I minus goes to I2, 2 there, 2 there, 2 lots of electrons there, 2 lots of electrons there. Therefore, this top one here, that one has been reduced, this one has been oxidized. Next, 4. When bromine is added to potassium iodide, Ki, the bromine is more reactive than the iodine there, or the iodide I should say, so we're going to get a nice little displacement reaction then where the iodine is left off by itself and you get potassium bromide being formed. Balance it, 2 there, 2 there. B, half equations, Br2 is going to the bromide ion, 2 lots there, plus 2 electrons here. We've got, it goes from an oxidation state of 0 to -1, that is reduction. And then in this one, we've gone from iodide to iodine, 2 there, plus 2 over there, we've got oxidation. Now, just because I've been a little bit daft, I've accidentally skipped B. I've gone straight to do C and D. So let's just do B down here instead. So you can see you can start either way around. You could do the half equations first or the redox equation, whatever you're comfortable with. I tend to prefer to do the half equations first. That's just something that my brain likes to do that way. But in this question, it's asked for it the other way around, so we should do it the other way around. So this section here is B. Here I've got the answer to C. And my answer to D is there with the reduction and oxidation thing. Okay, question 5. Which of the halogens gains electrons most readily? Should be abundantly apparent. It's the chlorine. That's too easy though. Let's give a justification. So for part B, it says explain your answer to part A. So what we need to do now is link that back to electrons and the distance between the nucleus and the outer shell, and the idea of the halogens having to attract extra electrons, just as we talked about right at the start of lesson 7. So what we need to put here is, there's quite a few different ways we can put it. Let's go for chlorine atoms are smaller first off. So in Elements of Life, we talked about the atomic radii. The atomic radii of chlorine is going to be much smaller than the atomic radii of bromine. Why is that the case? Because there is a small distance between the nucleus and the outer shell. Therefore, because of the sort of smaller distance almost between the nucleus and the outer shell, that means that the attractive force from the nucleus feels stronger. It is less shielded by the electrons between the nucleus and the outer shell. So we could say less shielding. Therefore, there is a greater attractive force from the nucleus, so it is easier to gain an electron. Okay, so part 6. So which of the halides, chloride, bromide and iodide, please bear in mind there that they are in the ionic form, not in the elemental form, which of these halides loses electrons more easily? Well, it's going to be a similar justification to what we had for part 5, but the other way around. So what we should see is it's going to be the iodide loses electrons more easily than the other halides, or the halides that we're talking about today anyway. Obviously, the further down we go in the group, the patterns will change a little bit more. So B, explain your answer. So in question 5, we talked about the chlorine atoms being smaller. Well, let's use that but the other way around. So in this case, iodide ions are larger than the other halide ions. Why is that? The iodide ions are larger because there is a greater distance between the nucleus and outer shell. Therefore, there are more electron shells between them, so therefore there is a higher degree of shielding. So other electrons are going to be pushing or somewhat negating the attractive force from that nucleus. So less attractive force is felt by the electrons from the nucleus, and therefore those electrons on the outside, they are not as tightly held. Therefore it only requires a little bit of energy to remove the outer electron. And this should sound pretty familiar to you because the justification for this is, yes, the same as in question 5, but also when we were talking about the reactivity of the alkali metals, alkali metal atoms, they have this kind of issue as well, that the further away something is from a nucleus, further away an electron is from the nucleus, the easier it is for that electron to escape. Okay, so that is question 6. Question 7. Now, question 7 is all about the reaction with silver. So, halides plus silver. Now, we know from Elements of Life, and potentially earlier down in school at GCSE, that the test for a halide is reacting it with silver nitrate being AgNO3. And the observation that you should see, we sometimes call it the milk, cream and butter test because you get slightly different shades of white. So here you can see the silver chloride is white, the silver bromide is a sort of off-white, and the silver iodide is a touch of yellow, but again, essentially off-white. So it's milk, cream and butter. So one's white, one is pale cream, and the other one is pale yellow. As we've discussed in the past, sometimes it's good to have a comparison of these next to each other as it makes it easier to judge, because if you just had one of these, it might be tricky to figure out which of the halides it is. But again, as we said before, we can actually use cyclohexane to help us with this because that gives us more distinctive results. However, the cyclohexane tests for the halogens are not necessarily always for the halides. It depends on how easily whatever the halide is bonded to is going to give up that halide ion. So back to the questions then. What do we get if potassium chloride is added to silver nitrate? Potassium chloride plus silver nitrate. We're going to get a displacement reaction happening. The chlorine is going to see that silver and would rather go with that. And the potassium is going to rather steal the nitrate. So you're going to end up, the only bit that we need to know about right now is silver chloride. So AgCl, silver chloride. And silver chloride is a precipitate, it is a solid, and it is an insoluble solid. The ionic equation, including state symbols for this reaction. So it says an ionic equation, therefore I do not have to have any spectators, so I can get rid of the potassium and I can get rid of the nitrate. I just want to have the silver ion reacting with the chloride ion to make silver chloride. We've got a plus charge of 1, we've got a minus charge of 1, that cancels out to give us a nice balanced ionic compound over here with our state symbols. So both of these are aqueous, and because it formed a precipitate, we can assume the state symbol there is S for solid. C, how do precipitates form from potassium chloride, potassium bromide, potassium iodide differ when ammonia solution is added to them? Now the solubility changes in ammonia. So what we should have got, what you should have researched, is the silver chloride will dissolve readily, and that's the terminology that examiners like. It dissolves readily in ammonia, NH3, whereas silver bromide dissolves less readily in ammonia, and silver iodide does not dissolve at all. So once again, we can get a bit of a distinction there between the different halides in our compounds by doing an additional test with ammonia. So let's have a look back at the specification references for the last few lessons. In lesson 7, we were supposed to categorise the physical properties, their appearance and physical state at room temperature. Done. The volatility, we saw that they were quite volatile, especially iodine, which had the ability to sublime. The solubility in water, and in organic solvents. We saw that they were way more soluble in organic solvents such as cyclohexane. Lesson 8. The relative reactivities of the halogens in terms of their ability to gain electrons. Done. The details of the redox charges which take place when chlorine, bromine and iodine react with the other halides, including observations and half equation, done through ES1.2. The reaction between the halides and silver ions in their precipitation reactions, and the colours that the precipitates go, and the solubility of the silver halides in ammonia, done again through ES1.2. So that is it for the reactivity of the halogens. Over the coming lessons, what we're going to be looking at is the discovery of the halogens and how we actually extract them from their source. I wonder what that source might be. There's a clue. The next job for you all is to make sure you know how the hydrogen halides are made. That was set in a previous video. Following that, we are going to do a mini test on the reactions and reactivity of the halides and the halogens. More details will be coming out soon about when those mini assessments are going to be taking place. For now, make sure your notes on the halogens are as beautiful as they can be, and I'll let you know when the next round of work is coming out. That's all, ladies and gents, girls, boys and others. Hope you've had a lovely time, a lovely day, and I hope you're all keeping well. Bye bye now.